All right, let's talk about something that is literally everywhere, but we almost never see it. It's this tiny, powerful workhorse that's behind almost everything that moves in our world. Yep, we're going to break down the amazing electric motor. Seriously, just stop and think about it for a sec. What do your electric toothbrush and a high-speed train have in common? I mean, besides being electric. There's this invisible force, right? A force that takes electricity from a battery or a plug and turns it into actual movement. So what is that force? Let's start small. Think about a kid's toy car. You just flick a little switch, right? And bam, it takes off across the living room floor. That sudden burst of speed, that's all thanks to a teeny tiny electric motor doing its thing. Okay, now let's scale it up a bit. Your kitchen blender. That thing needs some serious juice to turn your smoothie ingredients into, well, a smoothie. The blades spin at an insane speed, and that power, that relentless high-speed force, you guessed it, a much beefier electric motor is at the heart of it. And then we get to the big leagues, electric cars. These things are completely changing the game, right? They use these incredibly powerful motors to give you that silent, instant acceleration. That kick you feel is called torque, which is just a fancy word for spinning power, and it's strong enough to move a couple of tons of steel down the road. So from a tiny toy car to a top-of-the-line EV, believe it or not, the basic idea is exactly the same. So we've established this invisible force is pretty darn essential. But how does it really work? Let's pull back the curtain and get into the magic behind all that motion. Okay, at its heart, the definition couldn't be simpler. An electric motor is basically a magic box. You put electrical energy in one side, from a battery or the wall, and out the other side comes mechanical energy. And mechanical energy is just science speak for movement. Spinning, pushing, pulling, all of that is mechanical energy. So how does that magic box work? Well, it all boils down to just two core principles of physics. If you get these two simple ideas, you'll understand how basically every electric motor works. First up is something we all played with as kids, the law of magnetism. You know the deal. Take two magnets, the opposite ends, the north and south poles. They just want to snap together. They attract. But try to force the same ends together, like two north poles. It's like an invisible wall. They push each other apart. They repel. And believe it or not, this simple push and pull is the entire engine of the motor. Now, in a motor, we use two kinds of magnets. First, you have your permanent magnet, kind of like the one holding up pictures on your fridge. It's just always on. But the second kind is the real star of the show, the electromagnet. This one's special because it's only a magnet when electricity is flowing through it. And that's the key. We can turn it on and off. We have control. And that leads us straight to our second big idea, electromagnetism. This, right here, is the concept that changed everything. It's the simple fact that when you send electricity through a wire, a magnetic field just appears around it. Electricity creates magnetism, which means we can create a magnet whenever we want just by flipping a switch. That's a huge deal. Okay, quick recap. We know magnets push and pull, and we know we can make a magnet with electricity. Got it? Good. Now, let's put those two ideas together and build a simple motor from the ground up. All right, so any basic DC motor really just has two big parts. The first is the stator. Easy to remember because it's stationary. It doesn't move. It's the outer shell, and it has some permanent magnets in it, creating a steady magnetic field. And then, inside that, you have the rotor. Also easy to remember because it's the part that rotates. This is the spinning bit in the middle, and it's covered in coils of wire called windings. So, what happens when we hook up a battery? That's right. Electricity flows through those wire windings on the rotor. And remember our principle of electromagnetism? The second that current hits the wire, the rotor instantly becomes an electromagnet. We've just turned the spinning part into a magnet we can control. And now for the fun part. Our rotor is now a brand new electromagnet, and it's sitting inside the magnetic field of the stationary outer part, the stator. So what happens? Well, its north pole gets a big push away from the stator's north pole, and at the same time, it gets a massive pull toward the stator's south pole. All that pushing and pulling gives it a powerful kick, forcing it to spin about halfway around to line up. Uh-oh, we've got a problem. Once the north and south poles line up, everything is perfectly balanced. The forces are happy, the attraction is satisfied, and the rotor just stops dead in its tracks. So, how do we get from one little half turn to the continuous thousands of RPM spin you need for, say, a power tool? What's the trick to keep it going? Well, the answer is an absolutely brilliant piece of engineering. It's kind of like the motor's brain. a clever little switch called the commutator. This is the secret to the spin. Okay, let's walk through exactly how this little brain works. So, step 1, we send power to the rotor, and it becomes an electromagnet. No surprise there. Step 2, it spins halfway around as the opposite poles attract, just like before. But here's where the magic happens. Step 3, right at the moment it's about to line up and stop, the commutator does this incredible trick. It reverses the direction of the electricity flowing to the coil. And what does that do? Step 4, it flips the polarity of our electromagnet. The North Pole instantly becomes the South Pole, so the part that was just being attracted is now suddenly being repelled. And that gives it another powerful kick, forcing it to keep on spinning. I love this analogy because it's perfect. The commutator is always flipping the rotor's magnetic field at the exact right time. So the rotor is like a dog chasing its tail, or, a squirrel in a wheel. It's in this constant chase, always trying to catch up and align with a magnetic field that gets yanked away at the last second. And it's that never-ending, perfectly timed chase that gives us smooth, continuous spinning. So there you have it. We've created spin, or to use the technical term, torque. Now we just need to connect that spinning action to something useful and put it to work. And this brings us full circle, right back to the beginning. That spinning part, the rotor, can be attached to fan blades, the bit in a power drill, the drum in your washing machine, or, the wheels of an electric car. All those different machines are just using that one simple, powerful spinning motion we just figured out. Okay, that was a lot of physics, I know. So let's boil it all down to 5 simple takeaways. This is everything you need to remember about how an electric motor works. All right, let's run through them. Number 1, the big one. Electricity makes magnets. That's electromagnetism. Number 2, when you put magnets near each other, they push and pull, creating a spinning force we call torque. Number 3, the stator is the stationary magnet on the outside. Number 4, the rotor is the spinning electromagnet on the inside that tries to line up with the stator. And finally, number 5, the most clever part. The commutator is the switch that keeps flipping the rotor's magnetism to keep it chasing and spinning forever. It's pretty amazing, isn't it? From a simple science experiment almost 200 years ago to the very engine of our modern electric world. The motor has totally reshaped everything. And now that you know the elegant, simple secret behind that spin, it really makes you wonder, where is this incredible invention going to take us next?